Hi, this is Jeff Spencer, Math 120 instructor for the Community College of Denver. This is our video lecture over section 9b, which is linear modeling and linear equations. So a linear function has a constant rate of change and a straight line graph. Excuse me. So, a graph that is a straight line. So the rate of change is equal to the slope of the graph. Okay, so if you've taken an algebra course, you know that slope is your m from your y equals mx plus b. We also call it the rate of change in this class. The greater the rate of change, the steeper the slope. And to calculate the rate of change, by finding the slope between any two given points, we look at the change in the dependent variable, which is our change in our y, divided by our change in our x variable, our independent variable. You may have seen the y2 minus y1 over x2 minus x1. Same idea here. We're just describing it in a less algebraic way. You also might have heard that the slope or the slope is rise over run. Remember, dependent variable is our y, so that's our rise over our run, which is our horizontal change, our change in our x. So to find the slope of a straight line, you look at any 2 points and divide the change in the dependent variable by the change in the independent variable. So you look at these 2 points, and the change in the dependent variable is the y. So we just have to figure out the change from point 1 to point 2, this distance. Okay, so we subtract the 2 y's to get the change in the dependent variable. Then we divide it by the change in the independent variable, which is the x value. So that would be this distance. So you take the x2 minus the x1 to get that change. So a small store sells fresh pineapples. Based on data for pineapple prices between $2 and $5, the store owners created a model in which a linear function is used to describe how the demand, the number of pineapples they will sell per day, varies with the price. For example, the point $2 80 pineapples means that at a price of $2 per pineapple, 80 pineapples will be sold on an average day. What is the rate of change for this function? Discuss the validity of this model. Excuse me. So here is their model. So we can't answer this question until we see their model. And we see that if the price is $2, we'll sell 80 pineapples. And if the price is $5, that's the end of their model, that they will sell 50 pineapples. Because obviously if the price goes up, they're going to sell less pineapples because they're more expensive. So let's look at the rate of change. So we want to figure out the change in the y, which is the change in the dependent variable. So if we go from this point, we're going down 30. 80 minus 50 is a positive 30, but since it's going down, we're supposed to take the second point. 50 minus 80 is a change of negative 30. And because the demand decreases. And then the change in the price is just the 5 minus the 2, the $3. Okay, so we're taking the second point minus the first point. And so that's why it's a negative rate of change here, negative 30 divided by $3, 5 minus 2. And if we reduce that, we find that for every dollar the price increases, the number of pineapples sold decreases by 10. So a change in demand of $10, a decrease in demand, of $10 for every increase in price of $1. So general equation for a linear function. Let me show you. I have an example here. Sorry, I forgot about that. Okay. So the following situation involves a rate of change that is constant. Write a statement that describes how one variable changes with respect to the other. Give the rate of change and use the rate of change to answer any questions. So snow accumulates during a storm at a constant rate of 2.4 inches per hour. How much snow accumulates in the first 5.5 hours and the first 9.6 hours? So what statement describes this function? The way I see it is the snow is dependent upon time. So snow accumulated varies with respect to time at an average rate of change of 2.4. That's my answer. Time does not vary with respect to the snow, so both A and B are out. The snow accumulated varies with respect to time as this is the right answer. I see that these are the same, but the units are mixed up. So this is 2.4 inches per hour and 2.4 hours per inch. We know it's 2.4 inches per hour, so B is our correct answer. Okay. How much snow is accumulated after the first 5.5 hours? Well, if it's snowing at 2.4 inches for every hour, all I have to do is take 2.4 and multiply it by 5.5 hours. 2.4 times 5.5, we get 13.2 inches. Okay, and the same thing, if it's snowing at 2.4 inches per hour and we want to know how much snow after 9.6 hours, you take 2.4 times 9.6 and you get 23.04. 23.04 inches. Okay. And I think that problem is complete. Okay, oops, sorry, let's continue on. All right, so now we have the general equation for a linear function. The dependent variable, or y, is always our initial is equal to our initial value plus the rate of change times the independent variable. If you're used to your y equals mx plus b, this is what it looks like. Let me just relate everything. The independent variable is still the dependent variable is still our y value. The initial value we write it first. That's our b, what we start with. Sometimes people call that the y-intercept. And then we have the rate of change, which is our slope times our independent variable. So it's just in kind of, we put the initial value first, our b first. So the way we write it algebraically is y equals b plus mx. It's not any different. For example, the equation y equals 4x minus 4 represents a straight line with a slope of 4 and a y-intercept of negative 4. As shown at the right, the y-intercept is where the line crosses at the y-axis. So whenever you graph a line in the form of y equals mx plus b, you start with the y-intercept, that's negative 4, and then you do the slope. Well, the slope is 4. That means that it will go up 4 and over 1. So from this point, we go up 1, 2, 3, 4, and over 1. Up 1, 2, 3, 4, and over 1. Okay. The figure to the right shows the effects of keeping the same y-intercept but changing the slope. A positive slope is this a slope that goes up and to the right, meaning an increasing trend. That's what you see in pink there. A slope that is 0 is a model that shows no change, and that's our blue line there. And a slope that is negative goes down and to the right, shows a decreasing trend. That's our black line there. And then the figure to the right shows the effects of positive intercepts, an intercept of 0 and a negative y-intercept. These have all the same slope, but just if you have a positive intercept, it's on the top half of the graph. If it's a negative y-intercept, it's on the bottom half, and a 0 y-intercept just crosses right through the origin. So the function at right, use the function at right to describe an equation that describes the rain depth at any time after the storm began. Use the equation to find the rain depth 4 hours after the storm began. So what this is showing is that it looks like it's raining over a period of time, and it looks like it takes 2 hours to rain 1 inch, and then another 2 hours to rain another inch. So that would be a change. The vertical change would be 1 divided by 2. 1 divided by 2 is 0.5 inches. That's the rate of change, 0.5 inches per hour, because it rains. It rains 1 inch every 2 hours. 1 divided by 2 is 0.5. And as we want to find the rain depth 4 hours after the storm began, we could take that 0.5, multiply it by 4, and get 2 inches. Okay. So when we create a linear function, we want to find the slope and then get the y-intercept. And I'm going to do an example here, I believe. Okay. Following situation can be modeled by a linear function. Write the equation for the linear function and use it to answer the given question. The price of a particular model car today, or a model car, is $13,000 today and rises with time at a constant rate of $880 per year. So this could be like the Toyota Corolla. Each year the price goes up because of inflation and things like that. So, okay, so this year, let's say it's 13,000, and then next year it's going to be 880 more, and so on. So how much will a new car cost in 3.6 years? So the equation to model this equation, the equation to model this situation is what we have to fill in, where P is the price of the car in dollars and T is the time in years. So the price is dependent upon the time. So P is going to be my dependent variable. Let me make sure it's a lowercase p. P is my dependent variable, okay? And it depends on the time. Well, we write our initial value. We start with an initial value of 13,000, and then we add or subtract our rate of change. But since this is increasing, our rate of change is positive. So it increases $880 for every year. Okay, so we multiply the years by 880. Every year after today, it will increase by 880 added on to 13,000, which is what it started off with this year. So check the answer. Good job. And then we're going to figure out the price of the particular car in 3.6 years. That just means we plug in 3.6 for t. So I'm going to do 880 times 3.6. That's 3168, and then I'm going to add that to 13,000, and that's 16,168. So $16,168. Okay, so that's the type of problems you're going to be doing. Good luck. We'll see you next time.